Hello, friends. Continue our discussion about Java 21 upgrade. So, in the previous videos, we have covered chapter 1, in which we did Java installation and set up our project on IntelliJ, where we actually went with the Java 21 installation, how to do it, and then we installed Maven IntelliJ, and then finally we set up our project in IntelliJ using the Maven pom.xml. So, this was all covered. So, in this video, we will start with project Loom, in which the first and the most interesting topic is virtual threads, which is a part of JEP 444. So let's discuss about virtual threads in details. Just for the very formal definition of virtual threads, these are like lightweight threads, which are basically used for high throughput concurrent application. High throughput is the most important thing that is achieved by using virtual threads. And again, just going for the definition again, that it actually simplifies the thread per request type. We'll go through in details with the complete code example that how it is achieved. But let's go through the goals first. The second goal is that we are just going to leverage the java.lang.Thread API, which is the common API which is used for creating the threads pre-Java 21 version using the enable interface and using thread APIs, whatever. And the third goal is that using virtual threads, it's quite easy to actually our troubleshoot, debug, or profile. So all these type of keeping all these goals in mind, let's go into details that what do we mean by a high throughput concurrent applications. Let's try to understand what is the meaning of bandwidth, throughput, and latency. So I'm just taking an analogy of a water pipe. So if we call that it's for a thin pipe, the bandwidth or the capacity is less. And if we have got a very thick pipe having a bigger diameter, in that case, the capacity or the bandwidth would be more. So this is the meaning of bandwidth or capacity. Similarly, for latency, it measures the data speed, how fast the water which enters from this inlet, how much time it takes to go to the outlet. So it actually the speed with which the water in the from the pipe when it enters this pipe reaches its destination, which is the outlet. So this is called latency. And for the throughput, it's actually the speed, that how much amount of water we can run through the pipe per unit of time. For example, if we can transfer like say 10 liters of water to this pipe, say in 1 second, it means that the throughput is 10 liters per second. So this is how we define throughput. So when we say high throughput concurrent application it means that we are talking about this throughput, that how much amount of the data transmitted can be done in a specific per unit time. So this is what we can improve by using virtual threads. And here, the main important step is that we can use a simple thread per request type. So whenever we receive a new request from a socket client or whatever, we can actually create a new thread for each of the requests. So this is what we can achieve by using virtual threads. So every thread that we create by using the instance of java.lang.Thread. So it means that whatever the threads that we used before Java 21, which is not marked as virtual thread, this is by default a platform thread. And this platform thread is nothing but a wrapper over the underlying OS thread. So this OS thread are limited by the OS that we are using, of course, and each of these OS threads has got one-to-one mapping with the underlying CPU virtual cores. So if you look at this diagram, right? So if I go through this diagram, so in this, let's talk about this gray circles first. So these are actually the platform threads, which are the instance of java.lang.Thread. So each are actually, whenever we actually try to start when this thread is executing in a runnable state, what it does is that there is a OS scheduler. So there's a OS thread scheduler which will schedule this particular platform thread on the underlying OS thread. So there's a one-to-one mapping, and so the OS is actually maintaining all the scheduling. It can remove this whenever this is in a block state or a waiting state or when it's complete. So there's a context switch happening whenever this platform thread is unmounted from here, or it is removed from this OS thread on which it was working. And this OS thread would be actually one which is talking to the CPU cores, the virtual cores that we have. Whenever any thread is moved, this is called as context switch. And context switch is very expensive because what will happen is that all the thread caches and everything would be removed from that underlying OS threads on the multi-level CPU core registers and caches. So that's why Accordingly, for each of the context switch, it has been measured is that average 20 milliseconds cost. So that's why it is like very costly when we are using platform threads, and whenever there is a context switch, it means that this particular platform thread which has been running on a particular OS thread, that is removed, and some other thread is mounted, having a context switch on it, and another thread is running on this. So this context switch, we have to avoid it by using virtual threads. So by using this virtual threads, what happens now is that each of the platform thread will be still there, but it would be always be having a one-to-one mapping. So once we create a normal virtual thread, it's like very just like a normal Java object. It would be created, and then it would be just mounted or unmounted on this platform thread. So all this scheduling of these threads has been moved from this OS thread scheduler to inside this JVM scheduler. In other words, now whatever the OS scheduler has been doing, like to map this carrier threads, which is our platform thread, with the one-to-one mapping is still there for each of the carrier threads or platform threads. There would be a corresponding OS thread which is bound to it. But this is like just like a quite static one. So there is no context switch happening because right now one carrier thread is already like pinned to a particular OS thread. And now OS scheduler is just maintaining the threads which is maintaining here. But all those like mounting and unmounting of virtual threads on these carrier threads is done inside JVM now. It's not actually part of the OS scheduler. That's why this mounting and unmounting has got some cost, but it's just like much less than how it was costing there in the context switch, which was happening here at the OS level. All this like for the JDK scheduler at least uses full join pool, which is similar to that what it is used in our completable features API in asynchronous programming. So this actually has been like shifted, like all the scheduling process, the context switch which was happening here, that has been replaced with the inside the JVM for the mounting and unmounting of the virtual threads on the particular carrier threads. And this unmounting and mounting of virtual threads on carrier threads is much less in cost-wise as compared to the context switch which was happening here. That's why we say that it's quite fast to actually use virtual threads, because mounting and unmounting is quite less expensive than the context switches. So the new the dependency becomes like this: is that earlier it was platform thread which was having a wrapper over, just a wrapper over the OS thread. Now we have got virtual thread which can be mounted on a particular platform thread, and now that platform thread becomes a carrier thread. So this is the difference. This is just like having another lightweight process, and by having this design, right? So it's we can create lots and lots of virtual threads because these are very lightweight now, and mounting and unmounting, as mentioned, that it would be much easier, and all done inside the JVM, which makes it very fast. And now we can create like thousands and millions of threads without any dependency on how many number of OS threads are there, because that is always a limited number. It's always based on how much virtual cores that we have. Now this is all independent of that, because we can create multiple virtual threads, and each would be just mounted or unmounted on the certain number of platform threads. So as discussed, while a platform thread will monopolize a precious OS thread because it's like a wrapper over it, a virtual thread does not, because virtual thread is just like can be mounted or unmounted on the platform thread or the carrier thread. That's why the number of virtual threads can be very large, much larger than the number of OS threads. So enough of the theory now. Let's write some unit test cases to understand all these concepts that we have learned so far, and just go through it one by one. So I already created a virtual thread test class. So let's start with a very simple thing. Let's start with the normal platform thread, that how we create it. So I created. Let's talk about this first unit test case. What I'm doing here is that I'm just creating a new thread, which is the normal way that we create a platform thread, and where we are passing a runnable inside it as a constructor. So this is my runnable, which whenever I start this platform thread, it means that it will run this runnable code, which I have put as lambda here, and this would be running. And it will be also printing that I'm running inside this thread and giving the current thread name. And once I start it, so I just mark it as join, so that our main like unit test case doesn't finishes unless it completes this threads, which is just simply printing out that I'm running inside this thread. So let's run this first, a very basic, simple platform thread that we have been doing since Java 1.1. So I just click on the run button, so it should build, and then it will print the expected thread name. So I just run this. So, okay. So as it's shown that I'm running inside thread, and this is the thread name. This is our platform thread. We're having ID as 25, and the name by default is given as thread 0. Priority is 5, and the parent thread is main. So this is how we did it. It has always got a unique ID and a unique and this name and this 5. If I provide a name here as a constructor as well, then it will that this thread 0 would be like overridden with the custom name that we have given to this thread. So this is the first part, very normal, that how we create a platform thread and run it. Now let's talk about the second test case, which is exactly same as previous one. Here also we'll be creating a normal platform thread, but here instead of using this new thread and passing the runnable as a constructor parameter here, what I will do is that I will just use this thread of platform. This is a static method which is available in Java 21. So I will using this of platform, and then after that I will define my platform thread, and I will call it as unstarted because this is just a definition. I don't want to like start it immediately when I am creating it. That's why I'm using unstarted. And then I define the same thing that I am running inside the thread, same as this one, the renewable that we want to pass it to our platform thread. So once we create this as a definition, then again we call the start and join so that it runs. And so this will be having the same output as the first test case that we just saw. But the only difference is that the way that we are creating this thread. So here, as mentioned, that we are using new constructor, but here we are using thread.offPlatform and .unstarted. So let's run this and see how it goes. And the output should be exactly same as the previous one. Okay, so as mentioned that again, it is going to print the same thing as the first test case, where the ID is 25, thread name is thread 0 by default, priority is 5, and the parent is main. Now let's start creating our first virtual thread. I mean, so far we have covered platform threads. Now let's talk about virtual threads. So again, similar to like off platform, if you want to create off the virtual threads, we can call off virtual static method here. Everything should be same. I mean, I'm again creating this as unstarted and having this runnable as I'm running inside this thread. So here, I mean, as we discussed in the theory part, that virtual thread would be relying on the forejoin pool, which is the common pool which is created when we start our JVM application. So again, we have to do start and join, but everything is same except that we are creating a virtual thread instead of a platform thread here. Let me run this and we'll see the output. The output will be different because now we are using the common forejoin pool. So as mentioned here, now I'm inside this virtual thread, and this is the name of this virtual thread, having the ID same as 25. But right now, as we can see that it is using the forejoin pool 1 worker 1. This is different than what it was created for the platform thread, because virtual threads are relying on the common forejoin pool, which is created when we start our JVM. Okay, so this is what exactly same which is used by the forejoin pool itself and for the commutable future when we are using asynchronous programming with commutable futures. In that case also, it will be using forejoin pool. So this is how virtual thread is created, and this is how we can use it by just using this off virtual static method. Now this is just about one thread. Now let's try to create more than one thread. It's again very simple. It's actually the same process. What I'm doing is that I'm creating a runnable, but I'm creating a list of 3 virtual threads, and each of them would be like in the unstarted state, and then I will start each of 3 of them and then join it. So let's run this and see. So it would be actually using again the forejoin pool, and because it was run so fast, that is exactly the same worker thread which was used from the forejoin pool. Although you can see the IDs are different. So the first time it was ID was 25, then 27, and 26 for the 3 virtual threads. But it's actually because it's just a small, very, very simple line here. That's why it was used it was so fast that it only used the same thread in the forejoin pool, as is evident here. Okay. So this is about this creating multiple virtual threads. But here again, I'm just using off virtual method of the thread. Now let's do the main part right now. So what is the purpose of virtual threads? As we discussed that it is used for high throughput concurrent calculations. So here what I'm going to do is that I'm going to create like a new virtual thread per task executor. It's very much similar to that how we used to create the cache thread pool or the fixed pool before using the executor's static API. So here I'm going to create a set of virtual thread per task executor without any limit here. And what I'm going to do is that I'm creating an int string of range from 0 to 100,000. And for each of this range, I will submit this as a task. So there would be an executor with containing a lot of virtual threads. I think it's only it would be same as the number of CPU virtual cores we have. But still, even using those small number of virtual threads, still it would be able to execute it in a very fast time. So this is what we are going to see. So just for the runnable part, right? The runnable part is just that it will wait for like 10 milliseconds every time and then simply return it. We are not interested in this return, but it's just like we can just mimic it as a runnable task, which for every task it takes around 10 milliseconds. And once this is done, then we are actually doing a benchmarking here that how much time it took, and then we will notify the time here. So let's run this and see that how much time it takes for like 10,000 tasks to be submitted and to be executed by this, and each of the tasks would be taking 10 milliseconds to execute. So once we run this, let's see how much time it takes. Okay, so it took around 2.479 or around 2.5 seconds, you can say. And this is 2.5 seconds for 100,000 of tasks, which is submitted to this thread pool of virtual threads. Each of the tasks was taking like around 10 milliseconds. So it's a very good performance. Now let's talk about the existing cache thread pool, which was always there. So the way the cache thread pool works is that it will create new threads on demand. And so whenever there are like not enough threads available in the pool, it will create a new one to add to submit this task to. As we know that for the executor pool, there is a one common wait queue where the task would be submitted, and there would be some certain number of threads which would be taking all those tasks from that queue and start executing. So in the case of cache thread pool, it will take all these tasks, like there would be 100,000 tasks submitted, and each of the tasks would be having 10 milliseconds. It means that each time it will be creating the new threads in the pool to execute this task on demand. So this is what new cache thread pool works like that. So let's run this and see that what's the performance. So for the cache thread pool, we can see that its almost performance is slightly better than the virtual threads, but this is just for 100,000. If I further, as I mentioned, that this cache thread pool will be just using the platform threads. It will not create the virtual threads. So that's why, there's a limitation that how many threads we can create. So if I increase this sleep time to 100 seconds, or if I increase this from 100,000 to say 1 million, in that case, definitely the virtual threads, which are like much lightweight in the thread pool, that will have a better performance than the cache threads. But all this is good. But let's talk about the fixed thread pool now. As we know that if we create a new fixed thread pool of having say 16 threads, you can see that I have marked this as disabled, because if I run the same test scenario where we are submitting 100,000 tasks, each task having like 10 milliseconds, it will take ages to stop it. So if I just run this, it will take a lot of time. So if we just run this, the previous two versions ran in less than 2.5 seconds. It will continue on running for a very long time, because the idea is that there are only 16 threads available in the thread pool, right? So, and we are keep on submitting 100,000 tasks one by one. So very soon, like after say 10 multiplied by 160 milliseconds, all the 16 threads will be already occupied for running this 16 tasks. And now all the remaining submissions of this task for remaining 100,000, it will all be waiting until a thread is available in the pool. That's why every 16 times, there's a limit of 16, and every time it will be the next task in the queue has to wait until a thread is available from the thread pool. So as you can see that it will keep on running. That's why I have marked it disabled. So let me just stop it first, because it will be a lot of time. What I can do is that I can just change it from 10 to like 1 millisecond. And let's see. I think it will still take around 11 or 12 seconds to complete it. So this is like the amount of the throughput that we get improvements on when we are using virtual threads as compared to the fixed thread pools. So right now I'm running this. Let me just pause it. So I just fast forward it. As you can see that it took 12.55 seconds around. If I even reduce it to 1 milliseconds of sleep for each of the tasks. So definitely, as we can see that if we use new fixed thread pool, as we have been using for all our executor pool service, we always prefer to use fixed thread pool, but it has got a tremendous bottleneck or limitation for amount of for the throughput, for the amount of requests that we are submitting here. It will be having a bottleneck, and very soon our all 16 threads would be exhausted. Exhausted means that it will be busy completing one task, and all the remaining tasks after that 16 in the waiting in the queue, that has to wait until a thread is available. There is a slight improvement in cache thread pool, but still cache thread pool is always creating in the platform threads in our thread pool, and it will keep on creating new threads. And at a certain time, as we have learned, that these platform threads would be like a wrapper over the OS threads, and OS threads are limited. In that case, there would be a limitation that's at a time that it will just blow off, saying that not enough memory left, or out of memory error or stack error or whatever, because it cannot create those number of threads available. But all these problems are solved in this new virtual thread pools, in which a very small number of virtual threads can actually run lots and lots of submitted tasks in parallel, because it is just relying on that it's very smartly written. And first of all, it's very lightweight, and mounting and unmounting of these virtual threads over the carrier threads is very less expensive than the actual that how it works, but how it used to work before with the fixed thread pools or with the platform threads. So guys, this was a quick demo on how to actually use virtual threads, and we actually saw a glimpse of how using the virtual thread pool can tremendously improve the overall performance, or the by performance I mean the high throughput. Throughput is the most important concept for using virtual threads. In the next videos, we'll go into more details that what was the problem with the existing framework that we had for using the platform threads, and how virtual threads resolves all of that. We will learn more about the thread per request style of programming and I will take an example of a complete socket programming using blocking as well as asynchronous, all these type of parameters, all these type of design that we will discuss, and then we'll see that how we can improve the throughput of that application using virtual threads. So see you all in the next video.